When you see a giant container ship, you probably think it's basically an indestructible floating fortress, right? A huge island of steel. Well, it turns out even fortresses can break. Today, we're going to dive into the incredible science behind why these giants of the sea sometimes fail, and in some pretty catastrophic ways.
I mean, just look at this. A ship's hull is one of the strongest structures we build, so seeing a colossal gash torn into solid steel like this, it just makes you stop and ask, what on earth could possibly do that? How does a fortress of metal end up looking like a crushed can?
To figure that out, let's put on our detective hats. We're going to treat this like a forensic investigation, sifting through the evidence to find the culprits behind these massive failures. So, let's get started.
Okay, so what exactly are we looking for in this investigation? What are the prime suspects when a ship's hull just gives way? As you're about to see, it's not always some big, dramatic event. Sure, sometimes it's the stuff you'd expect, but a lot of the time, the real culprits are way more subtle.
All right, let's start our investigation with the most obvious culprits. We're talking about the sudden, violent events that cause immediate, massive damage. The stuff that makes headlines. So here's our lineup of the usual suspects. First up, you've got overload. That's just brute force damage from things like a collision or running the ship aground. Then there's inappropriate design, which basically means the ship was never really built to handle the real-world stresses it was going to face. And finally, you have poor workmanship. Because, hey, a ship is only as strong as its weakest link, or in this case, its weakest weld. And this right here is a perfect example of what we mean by poor workmanship. I mean, look at those welds or that misaligned plate. It might seem like a small detail, right? But these little flaws create hidden weak points in the structure. They're basically the perfect starting line for a tiny crack that could, one day, tear the whole hull apart. But this is where our investigation takes a really interesting turn, because the biggest dangers aren't always the big, sudden ones. What if the real enemy is silent, invisible, and has been working to destroy the ship from the moment it first touched the water?
And that brings us to our next line of inquiry. We're now hunting for enemies that work slowly, over years and millions of cycles. We're talking about the hidden dangers of time and repetition. So we have two new suspects on our list, fatigue and corrosion. Think of fatigue as a mechanical problem. The steel itself is literally getting tired from being bent and flexed over and over again. Corrosion, on the other hand, well, that's a chemical attack. That's the ship slowly but surely rusting away as it fights against salt water and air. The best way to understand fatigue is to think about a paperclip. You bend it back and forth, right? It doesn't break on the first bend or the second, but each little bend adds a tiny, invisible amount of damage until suddenly it just snaps. A ship's hull does the exact same thing with every single wave it plows through. This graph shows that process. Even a little bit of stress, if you repeat it millions of times, will eventually cause a failure. A fatigue fracture is kind of like a slow burn disaster. It happens in 3 stages. It all starts with initiation. A microscopic crack forms maybe at some tiny defect from when the ship was built. Then comes propagation. With every wave, every vibration, that tiny crack gets just a little bit bigger, spreading silently through the steel. And finally, it gets too big. That's when you hit failure. The steel can't take the load anymore, and the break is sudden and catastrophic. And then there's corrosion's nasty attack. It doesn't just happen evenly across the surface. No, it starts as these tiny little pits, just like you see in the diagrams on the left and that real-world picture on the right. Each one of those little pits becomes a focal point for even more damage, weakening the entire structure, plate by plate. Now, here's where things get really, really dangerous. These two culprits, they almost never work alone. As this diagram shows, they actually feed each other in this vicious cycle. Stress can crack a ship's protective paint, which lets corrosion get in. Then, as corrosion creates those pits and weakens the steel, it creates new places for stress to build up, which makes the fatigue even worse. It's a terrible partnership.
So, this brings us to the real heart of our investigation. We've seen the what, overload, fatigue, corrosion, but now we need the why. And the smoking gun, the one thing that connects so many of these failures, is the science of stress itself.
The key idea here is something called stress concentration. And here's the best way to think about it. Imagine you're pulling on a flat sheet of rubber. The force spreads out nice and evenly. But what happens if you cut a tiny notch in it? All that pulling force is going to focus right on the tip of that notch
and it'll tear super easily. Well, in ship design, certain shapes and connections create the exact same kind of problem, creating what are essentially engineered weak points.
And this slide, wow, this is the big payoff of our entire investigation. On the left, you see a design diagram for something called a hard point. See how it creates that sharp angle? Stress can't flow smoothly around it. And on the right, the devastating result, a real-world crack starting from that exact spot. This is the theory made terrifyingly real. This leads us to one of the golden rules of building ships, a rule so important they literally write it in all caps. You never ever place a weld, which is already a change in the material, directly on a spot where stress is already being focused. I mean, doing that is basically sending an open invitation for failure. So, our investigation is pretty much complete. We know the problem. But how do you solve it? This is where really clever engineering comes into play, designing ships not just to be strong, but to be resilient against these very forces. The challenge is pretty clear, right? If these points of high stress, these hard points, are the starting line for catastrophic cracks, how do you design a structure that just gets rid of them? How do you smooth everything out? And here are some of those brilliant solutions in action. Instead of just letting stress pile up at a sharp corner, engineers have figured out ways to spread that load out. You can see how they add extra supports, or extend a bracket to soften the angle, or even fit reinforcement pads. It's all about giving that stress a much smoother path to follow and getting rid of those dangerous bottlenecks. So if there's one key takeaway, it's this. Modern ship design isn't just about throwing more steel at a problem to make things stronger. It's about being smarter. It's about anticipating where failure is most likely to start and then engineering those weak points completely out of the system from day one. And that kind of leaves us with a final thought. We've looked at the culprits, the science, and the solutions. But building these incredible structures is this constant battle between physics, economics, and the raw power of the ocean. And it's a good reminder that in this high-stakes game, the work of making things safer and stronger is never, ever really done.